So welcome along to today's talk in the IoT Capstone project. And in this talk today, what we're going to be looking at is spatial data and how that might play a role in what you're doing, but also more along the lines of some of the ways that we can go about using it and thinking about things from a spatial perspective. So let's jump in and see how we get going. Probably the first thing I want to point out is what spatial isn't. Now this is actually important because even just a couple of days ago when I was telling somebody what I did and I said I work in spatial sciences, they started to ask me about NASA and space travel and all kinds of things, to which I really have no idea, except I'm also a big Star Wars fan. So that's where things for outer space and that kind of stuff end for me. So when we look at things like this, many people think of spatial as only maps. Now these certainly contribute to spatial, but it is a lot more than that. It's things like GNSS, which is Global Navigation Satellite Systems, where they provide us with exact positioning. Most of us think of this kind of thing as GPS, but GPS was actually a particular type of global navigation system that came out of the US. So GNSS is actually the overarching term of which GPS falls underneath it. Now, the more accurate we know where objects are, the more detailed we can start to work with them. And in one sense, sometimes the more automated we can work with them. Now, anything spatial relates to location, and you are always somewhere. However, that influence of location in the past has been omitted. Now, there's a tremendous amount of spatial data that exists, but where it becomes really helpful is where we start to combine it and use it in relationship to other data. Spatial data has many different ways for it to be represented and stored. And you can see here, we've got these three maps in front of us, and this map here, this map here of the London Underground, now that map in and of itself is considered to be the most used map in the history of the world. So spatial data is something that actually affects and influences all of us because we are always somewhere. So spatial science, well, really touched on it already. It involves a whole range of different disciplines, and its focus is one thing and one thing alone, and that is location in relationship to the Earth's surface. And there's a whole bunch of things that fall in and under that. It's important to keep in mind that everything happens somewhere. Yes, everything happens somewhere. And I know you're going, oh, David, we know that. Yeah, you do, we do. But it's only in the last few years that we've really become quite adept to using this kind of information to help us process things. So when I say we're become adept more recently in using this kind of data, I know mapping data has been used for a long time, but now, particularly in the age of Google Maps, Apple Maps, and these kinds of things, we've started to become extremely adept at being able to use this data to generate new knowledge and new understandings. So spatial thinking is something that is extremely crucial. We need to think in a spatial manner. Now, spatial thinking is based on this constructive amalgam of three elements: concepts of space, tools of representation, and processes of reasoning. It is the concept of space that makes spatial thinking a distinct type of thinking. By understanding the meaning of space, we can use its proximities. We can use the properties, the proximities of things around us. We can look at dimensionality, continuity, separation, these kinds of things. We can actually use it as a way to structure problems. Once we've structured problems in a spatial manner, we can start to solve those problems or look for solutions in a spatial manner. It gives us a way to express and communicate solutions. Now, as we start to express relationships within spatial structures, things such as maps, multidimensional scaling models, computer-assisted design, and renderings, by doing this and expressing things in this way, it actually gives us a way to perceive, remember, and analyze static things. We can use transformations, and through these transformations, we can often perceive the dynamic properties of objects and especially the relationships between different objects. This is all spatial thinking. So to think spatially entails us knowing about space, relationships among units of measure, different ways of calculating distance, the basis of coordinate systems, and the nature of spaces. We might have to think of things. Are we talking kilometres or miles? What about calculating distance? Do we think of how many miles or how many kilometres? How long it took to travel? Or actually how much it cost? With coordinates, we have to think of things such as the Cartesian coordinate systems, or maybe we're talking about polar coordinates or grid coordinates of a specific area. We might have to think when it comes to the nature of a space, are we thinking about it in a 2 or 3 dimensional manner? And these are crucial. Thinking spatially also means we have to think about the representation. What do I mean? Relationships among views, projections, and what's the effect of different types of projections. And then we even throw in graphic design. How do we represent it in a graphical way? So when it comes to things, we have to think of plans when we're thinking of plans versus the elevations of buildings. There might be orthogonal versus perspective maps. There's Mercator versus equal area map projections. Then there's also this role when it comes to graphic design of legibility. What are the visual contrasts that allow us to see things and to see things well? This is still spatial thinking. When it comes to reasoning, we need to think through the different ways that people think about the shortest distance. Is it, as we say here in Australia, as the crow flies, versus a route distance in a rectangular street grid? We might have to think of projecting a functional relationship on a graph into the future, or estimate the slope of a hillside from a map of contour lines. We have to be able to extrapolate and interpolate. And importantly, making decisions. We make decisions spatially all the time. If you're someone who drives a car and you listen to the radio and get traffic reports, or you follow a Twitter feed. You make decisions spatially. We might select an alternative route. If you have public transport and you have public transportation apps, they tell you where the buses are. You're spatially thinking, should I take this bus or should I take that bus? Which one is going to get me there faster? So I want to now talk about Jon Snow. And you're looking at this and going, David, how does Jon Snow fit into it? Well, I'm not talking about this Jon Snow, but this Jon Snow. Now, Jon Snow was a revolutionary spatial thinker. And you go, David, why was he so revolutionary? This is the first time I've ever heard of him. Well, in London in the 1850s, people were dying of cholera. Now, cholera is a waterborne bacteria that kills people if it's not treated. And back in those days, it was a very common form of death in London. Now, what he did was he looked at maps. He looked at the public taps that existed in London, and from that, he mapped where they all were, and then he mapped the deaths, cholera deaths, in relationship to those taps. Basically, you could say he worked out which were the death taps, and they were able to shut those taps down. Now you're going, that sounds like a pretty straightforward kind of thing, and in our day and age we would say it is, but in 1854, this kind of thinking had never occurred before. So, what was he doing? Well, what he discovered was there were different death rates for cholera in different parts of London. Now, there were two water companies that supplied London with its water, and it was supplying it from two different sources, one from the River Thames and one from aqua resources outside of London. So we had drinking water coming in to places from the Thames. Now, that was not good because that's where everyone pumped everything you can possibly imagine into. So, what he was looking at was who's supplying the water to where. But this wasn't possible to know. The water companies didn't know which taps were being supplied with which water supplies. And what he did was he was able to calculate and correlate a death rate from certain taps of 5 per 1,000 people who used it, and from other ones up to 71 people died per 1,000 who used it. And what he was able to do was actually infer and spatially analyze what taps were being supplied by what water companies. Now, this was extremely revolutionary. So we say Jon Snow was the very first spatial scientist. And that may be arguable, but in our terms, that's what it is, or what we perceive him to be. So there's three functions that spatial thinking take. A descriptive, where we start to capture, preserve, and convey all of the appearances of and the relations that exist amongst the objects. We're able to take an analytical look at things. We're able to understand structures of objects and their relationship to other structures and objects. And then comes what I find the most exciting one, when we start to be able to infer things. We can generate answers to questions about the evolution and function of objects, just as John Snow was able to infer which taps in London were being supplied by which water companies. So when it comes to us, how does this all tie in with IoT? You're going, David, great, that sounds wonderful. But what about us? Well, it's really important. IoT has a lot to do with location. We're starting to build things with sensors in them. Our devices, our things that we're creating, we know where they are. What are they doing? So it becomes important to understand or to start thinking spatially. What can we learn? So when we're doing things, we need to, and when we're building our devices and what we're doing in IoT, we now need to start to go, what do we want to do? What do I mean by that? Well, we need to think through what it is we want to do. We have to think, when do we want to do it? What resources are available? And how might we do it? So you're going, David, I know I get this, but I'm not quite sure. Well, our IoT devices have some limited capabilities. Yes, we can have huge amounts of power in things like our phones. We've got more power in our phones than we put man on the moon. But we are now doing more and more things, and we're generating more and more data. With the more power we have comes more capabilities and the desire to collect, store, and process larger amounts of data. So we need to think through, what are we doing? What is our IoT device doing? When it comes to spatial, what do we want to do with the spatial information? And now I ask the question, when do you want to do it? What do I mean by that? When do you want to do it? Do you want to do it in real time, or can we collect data and then do an analysis? What resources do you have available? What's the size of our devices? What's the capacity? And then we're thinking through, how are we going to do it? Are we going to do it on device? Are we going to process the data elsewhere and generate visualizations on the web? These are the kinds of things we need to think through. So when it comes to doing this, GIS, as you've heard mentioned, Geographic Information Systems. Now there's two major geographic information systems that are usually mentioned. One is produced by Esri, and that's their name products are ArcGIS, ArcMap, ArcGIS Pro. There's several of them. Now these are proprietary, this is proprietary software. It is extremely powerful software, but it can be expensive. And we have to look at things and go, is this what we're after? They do some fantastic stuff. The other package, which is often used or often talked about, is one called QGIS or QGIS. And it's very similar to some of the Esri products, but it's open source. So the source code is there, available, and there's a really large developer community around it. It's also very powerful. You can do a lot of stuff with QGIS, and it comes at no cost. Keeping in mind, you will always have trade-offs. Esri, proprietary and cost, comes with support and all kinds of things that you get through Esri. QGIS, open source, no cost, but you're relying on the community to help you out when you get stuck. So some things to think through when you're making decisions. What are some more possibilities that we might have when it comes to GIS, and processing spatial data. Let's take a look at some now. So there are spatial database management systems. I would assume that most of you are familiar with relational database management systems, but there's also spatial database management systems. And all it really is a software package that often works with an underlying DBMS, but it specifically supports spatial data models. It works with some of the spatial abstract data types, as well as a query language from these abstract data types. So it's providing us, similar to what I would say a normal database management system, but it's got that spatial aspect to it. It supports spatially indexing our data. Usually, it has efficient algorithms to allow us to process spatial operations. And this is important because spatial operations can actually be quite large. We start to look at, we want to do something in this certain area. Give me all the information in this area. Now that can require a lot of processing. So an example is PostGIS or PostGIS, which is an extension to the Postgres SQL database. And obviously PostGIS works with Postgres SQL. Now, it has spatial data types, polygons, and there's operations. We're looking at things such as operations that are callable from SQL3. Which are things like overlap. Does this overlap with that? Because in the spatial realm, that's really important to understand. Do we have an overlap? Because when we have an overlap, that may mean we need to look at doing things differently. Spatial indices, R trees, R plus trees, GIS trees. These are all the things that a spatial database management system provides us with. So we talked here about PostGIS and Postgres SQL, but there's also Oracle. Now, Oracle now has a spatial aspect to their database. You have to buy it separately as an add-on, but Oracle is now developing its own spatial database management system. So what's the difference and what are things to be thinking through? Well, our traditional database systems gives us these things: persistency, concurrent access by multiple users, scalability, and efficiency when it's non-spatial queries. They're the traditional things. Now, building our spatial database management system on top of that, we usually get all of those things as well. But it can take it further. We can start to go with some spatial queries. So we've got the non-spatial query, list the names of all the bookstores with more than 10,000 titles. But I might want to go list the names of all the bookstores within 10 kilometres of the city of South Perth. Now that's a very different kind of query. We might want to say, list all the customers who live in the Perth metropolitan area. So instead of going, give me the top 10 customers, I want all the customers who live within the Perth metro area. And then I might even want to scale that further and go, give me the top 5 customers from the Perth metro area. And because of the nature of that kind of query, a spatial database system is really helpful. So PostGIS, it's an open source library of functions and data structures, letting us use PostgreSQL database to be a spatial vector database. I say here it implements the OGC Simple Feature Model for SQL databases, and you're going, what is the OGC? It's the Open Geospatial Consortium. Now, this is a worldwide consortium that actually sets and defines the standards for geospatial data. So, there's some more things as to why PostGIS is useful, and it's a great database and system. And here's some examples of, or an example I should say, of what some data might look like within the database. But I want to draw us back to we're dealing with IoT. And where are we going to be storing or having our database? This becomes important. Are we having our database on our device? Are we having our database off the device? Is it a combination of the two? Are we keeping the data? Are we getting rid of the data? Are we overwriting the data? These are important because of the limited resources within our devices. And we have to be careful to manage the resources well. We want to have low power usage. We want to have maximum uptime. And in doing that, we have to manage the resources really well. And this is where we come back to that thinking through, where do we want to process our data? Where do we want to be storing it? How do we want to be storing it? So let's have a look at another very common format for storing information. And that's JSON, which is the JavaScript object notation. It's not complex, it's not complicated, but it can develop that way. What do we have here? Well, we have something, we've got a name, David McMeekin. And then we've got teaching partner, and then open curly brackets. And then we have some more information. So you can see we're sort of developing here with our open curly brackets and then another set of curly brackets. We're starting to build a hierarchical type of object. So we have a name, and that name has a value, David McMeekin. We have another, what I'll say, key in teaching partner, and then teaching partner has two more keys, TP name, which we assume would probably be teaching partner name, and teaching partner email. And there we've got information in it. So JSON is a really, I would say, simple format to store data. And beyond being simple, it's becoming one of the most common ways that data is stored and then passed around the World Wide Web. Now we can take JSON one step further, and we take it this one step further into being what's called GeoJSON. Now GeoJSON is really just the geographic version of JavaScript object notation. Now you will see that when people save files in the JSON format, they'll often save it .json, and when they save it in the GeoJSON format, they'll save it .geojson. Right up front, it doesn't matter. You can save it as JSON or GeoJSON. It does not matter. So what's GeoJSON? Well, it's just a format that allows to store geographic data as well as non-spatial attributes. So it supports these geometries, the geometries of a point, a line string, a polygon, a multi-point, a multi-line string, and a multi-polygon. So we see here a sample GeoJSON file. We've got a type, which is a feature, then we've got a geometry, and then the geometry has a type, which is a point, and this point has coordinates. And we continue on. This, whatever it was, this geometry has properties. This property, or one of the properties we've got, is name, and it's called spatial sciences. And when we take that little bit of code, or that GeoJSON code, and we pop it in this GeoJSON visualizer, there we have a visualization of that code. And you can see the icon there in the middle, and that's the locator, and that's where we are. And it's actually the Spatial Sciences building on the Curtin University campus. Now, thinking this through, going back to those questions I was asking, GeoJSON becomes a great way for us to think about storing our data on our IoT devices. And we'll come back to that. What does it have? It has a point. Which are the coordinates of a single position? There's a line string, which is two coordinates or two or more coordinates, and you can imagine it's a line string. Now, a polygon, these are just coordinates that make a linear ring. And with a polygon, it's really important to note that your first set of points and your last set of points need to be the same, because a polygon must close. There's multi-points, which is just an array of positions, a multi-line string, which gives us coordinates of an array that make a linear string. And there's multi-polygons, and that gives us an array of polygons. Reasonably straightforward. So here's some sample GeoJSON code. We've got a type, we've got a line string, and we've got a polygon. And you'll notice with our polygon that our first two coordinates and our last two coordinates are the same. And there's some more visualization of our GeoJSON. Now we're visualizing that on a huge scale, but we can drill down to a much more granular scale. And we can even develop our own coordinate system. We can create a grid system, and we could build that grid system to be within an environment, let's say, of a room. And that room would have its own grid system, and then we can operate off that grid system for location and identifying things within that space. So GeoJSON has these extra things, a geometry collection, there's feature and feature collections. So they're just ways that we go about representing things in GeoJSON. Now it's important to note GeoJSON is a really straightforward text-based format, which means it may turn out to be very lightweight and something that we might want to be considering using. So it's a simple text-based format. I've already jumped ahead of myself. It can be lightweight. It's easy to move around if we move it around reasonably quickly. What do I mean by that? Well, as you would know, you can create a file and let that file collect data, and it will grow and get large. But we can pass these files around, small files, around our systems for processing. And GeoJSON is an extremely simple language or simple data format to parse. So when I think of processing this data, I think in the forms of Python. Now, the thing that makes JSON or GeoJSON really cool is it looks a lot like a Python dictionary. Now, Python provides some amazing libraries to work with this kind of data. One of the libraries, which is my favorite, or one of my favorites, is the JSON library. Now, the JSON library, when you import that into your Python code, with a single line of code, you can take an entire GeoJSON file and convert it to a Python dictionary. And once it's in that Python dictionary format, you can start to manipulate it and change it and analyze it and extract information and knowledge from it. What are we finding out from our devices in regards to location? Really important. So a quick look. If you're going dictionaries, I'm not sure what dictionaries are. Well, in Python, a dictionary is just an object that stores data. That's it. It's like a dictionary. There is a key and a value. We use our key to find the value, and we call them key-value pairs. Just like a dictionary, there is a key, which is the word, and the value is the meaning, the definition. And that's the same when it comes to Python dictionaries. Simple to use, very powerful. In conjunction with JSON and GeoJSON, really, really, really powerful. And there's just a little bit of an idea here of how you might go about creating a dictionary within Python. Now, don't be overly concerned about the code if you're going, I'm not sure about it. If we need some Python code, we can generate that Python code. But I just wanted to start to touch on those things a little bit. And here's some more sample code of us creating a dictionary in Python. Now, I've left these here, or I've got them in here, so you can see it's not difficult. And it's not difficult either when we start looking at pulling in GeoJSON files. So the last two things I want to talk about when it comes to processing this kind of data within Python is Pandas, and there's also a GeoPandas library. Now, these are libraries, or the Pandas library is used in a lot of data analysis, and it gives some really powerful tools for processing data. And there's all kinds of things that happen and we can do with it. Now, you're going, David, that's not spatial data. Yeah, correct. But based on top of Pandas is GeoPandas. Now, GeoPandas is fantastic for working with vector data, spatial vector data. It's based on Pandas, and it provides us with some, what we would call some objects, two data objects that we can use to process data or process spatial data. Very cool and fantastic. So it gives us the things we need for geometry kinds of calculations and works. Geometry being, in this case, related to the Earth's surface. So I want to bring it to a bit of a close and ask you some questions. Why do you need location when it comes to your IoT device? Why is that important? Is it actually important? Really crucial that we answer that question, because with our devices, we don't want to collect data that we don't need and we won't use. How much location do we need? How accurate does the location need to be? The reason that's important is often the more accurate the location that we need, the more drain that is on our resources such as power or battery. Processing the data. Are we going to process the data we collect on the device, or are we going to take it off the device and process it elsewhere? Where do we want to visualize it? What do I mean by that? Well, now we've got this location data. Where are we going to visualize it? Are we going to visualize it on the actual device, or are we going to visualize it somewhere else? For instance, a web interface that allows us to see what's going on. Really crucial to think through. And once we've thought through these things, we have to go, well, what can I actually live with? What is enough? What is good enough? How accurate? All of these things, because you can go, oh, David, I want to have location. I want it accurate to the millimeter. I want to process it on the device, and I want to visualize it on the device. But is that necessary? What can I live with? And how can I make my IoT device and location relevant to others so they can see what it's doing and they can draw information and answer their questions from that? So we've covered quite a bit, but I want to leave it here, turn it back over to the rest of the team, and I hope that this was helpful. It was thought-provoking, and if you have questions, please get in touch with me. Thanks very much.